So welcome everyone. So the first talk of this morning session will be delivered by Sarfraj Fency from ICTS Kolkata, and he will talk about optimal speed of quantum control in open quantum systems.
Hello, thank you. So good morning everyone. My name is Sarfraj and I am from Indian Institute of Science Education and Research, Kolkata. And the work today I will be talking about is optimal speed of quantum control in open quantum systems. And this work is done with collaboration of Dr. Riddhi Chatterjee, who is a postdoctoral fellow at IISc Bangalore and under the supervision of Professor Ankit Bhattacharya. So let me begin by clearing the motivation behind this work. So in quantum technologies, one of the primary goal is to achieve high precision and fast manipulation of quantum systems. So let's say I want to evolve my system from plus Z to plus Y. So it matters how fast can I do and how close I can get to my target state, which is plus Y. But there is an inherent bound which comes from Heisenberg uncertainty principle, which is quantum speed limit, which sets the theoretical minimum bound on how fast can I evolve my quantum systems. And when you consider the practical situation in which environmental dissipation also comes in, it complicates the situation even more because there is noise involved and the trajectories are not very well defined. So to mitigate these challenges, one of the thing which people try to do in experiments is to apply shorter pulses, means pulses for short duration. And if you apply pulse for short duration, you have to apply it with higher power. Okay, but there are several papers like this experimental paper. These are theoretical paper which show that if you apply a drive, which is the external pulse, with very high power, it leads to another source of dissipation, which is called drive-induced dissipation. So the very act of preserving dissipation is introducing another source of dissipation. So the primary question which we ask is that if we introduce drive-induced dissipation, how will it affect the quantum speed limit? And given that there are these sources of dissipation which are coming from environment and from drive-induced dissipation, can we achieve fast and high fidelity quantum operations? And can we design an optimal control strategy to mitigate these challenges? And to answer this question, we have our simple model which consists of a two-level system. So here capital omega is the Lama frequency and sigma z is the Pauli z operator. And we apply a time-dependent external drive on the system. So here you can see that drive is applied along x and y, and their amplitude u1 and u2 are time dependent. And it is oscillating with a frequency omega. Now, since this is an open quantum system, we model the thermal bath as a two-level system. And here omega SL is the strength of the coupling between system and the local environment. And to solve this problem, the mathematical formalism which we use is quantum master equation. And in the standard master equation, if you see, consider the Bloch equation, Redfield equation, or the Lindblad equation, standard Born-Markov equation, all consider the environmental dissipation into account, but not the dissipation from other sources. So as I said in the previous slide, there is a dissipation which is coming because of application of strong drive, which is drive-induced dissipation, and this standard master equation failed to take into account that. But this paper, this is theoretical paper, and the claims were verified experimentally in this paper. It gives a formalism to introduce the dissipation from strong driving. And there are other several theoretical papers which show the existence and implications of drive-induced dissipation in several architectures like quantum information, quantum foundation, dipolar coupled system, quantum optics, and many more. And the formalism which I'm talking about is this fluctuation regulated quantum master equation. And this was introduced in the first week of this conference on Friday, I think 24th, by my professor, Professor Ankit Bhattacharya. So if you want more details, please refer to that, because this is not about that. I'm just using this. So here you can see, if you consider just these two terms, like the first order commutator, so this gives the oscillation. And the second order term, this double commutator, gives you the dissipation. Now, if you forget about this exponential kernel e to the power minus tau by tau c, this has exactly the same form as Born-Markov master equation. But the very act of introducing this kernel allows you to treat external drive in the second order and calculate the dissipation from it, and also from other sources. So here H effective is any general Hamiltonian, not only the system environment or the environmental dissipation. So given that, using this master equation and our model, these are the dynamical equations. This is the dynamical equation I come at. And here, everything is scaled with respect to system path coupling, which is omega SL. So this entire equation is dimensionless. So now here, focus on this blue box. This gives me the oscillation contribution or the first order contribution from the external drive. And this red box, this gives me the environmental dissipation, which has the standard Lindblad form. And if you consider these two boxes, blue one and the red one, this is what has been considered in the literature so far. And our contribution is this one. So here you can see this term, first term, is basically the drive-induced dissipation. This entire term is coming from treating the drive in the second order, but specifically this first order, first term has the Lindblad form. And second term, this is coming because, one of the advantages of FRQMA is that you do not need to apply rotating wave approximation. You can treat the entire Hamiltonian into consideration. So when we take the entire drive Hamiltonian, we get this term, which is the second order contribution, and this is coming because of treating the drive in the second order. And this has some non-Lindblad form, and there is detuning. This delta minus is basically the difference in the frequency, this one, the frequency of the drive and the Larmor frequency. So one of the questions which we ask is to design an optimal control strategy. And for that, we use GRAPE algorithm, which is well known in the literature. So it stands for Gradient Ascent Pulse Engineering. So let me give you a brief introduction for it. So in GRAPE, one of the primary requirement is to discretize the time into n steps. So here, let's say I have time from 0 to capital T. So I have to discretize into n steps of step length delta T. So since my drive Hamiltonian is also time dependent, it will also get discretized. So let's say when I say first step, what I mean is from T0 to T1. And similarly, nth step is from Tn minus 1 to Tn. And it is assumed that in this specific time step, the drive Hamiltonian is constant. It can change for other steps for not that particular step. And with that, this is the Hamiltonian for the jth time step. So here H0 is the bare Hamiltonian, and this is the discretized version of the drive Hamiltonian. So here you can say this U, K, J are basically the controls. So I'm applying the drive along sigma X and sigma Y. So I have two controls, but in principle, you can have multiple controls as well. So now how to apply GRAPE algorithm? This is simple. You define an initial state and a target state where you want your system to go. And then you have to create a drive Hamiltonian with initial guess. So here, this drive Hamiltonian, you have to assume initially, you have to guess the value of UKJ. And if you have some educated guess, well and good. If not, you can take the guesses like we did. We have considered it as 2 pi, 2 pi. You can have it unequal as well, pi, 2 pi. So far, our analysis shows that it is not very sensitive on the initial condition. Then you have to evolve the system using FRQMA, the dynamical equation, which I showed few slides back. Then you have to calculate fidelity. So fidelity basically tells me how close I am to my target state. So fidelity of 1 tells me I'm exactly on my target state, and fidelity of 0 tells me I'm miles apart. So fidelity ranges from 0 to 1. Our goal is to maximize the fidelity, and for that we use an optimization package. So for my work, I have used Julia. So we have considered Optim package, but if you are using some other language, you can use any optimization package. Then it calculates the gradient at each step, and the next step is in the direction of minimum gradient in the parameter space of drive strength. Then you get a pulse profile. This pulse profile is used as a guess for the drive Hamiltonian, and this process is repeated until we maximize the fidelity. And with that, these are the results. Yes. So here on the x-axis, you can see that I'm plotting the pulse time, that for how long I'm applying the drive. And on the y-axis, it's fidelity. So here I'm showing this for the initial state is plus x, and my target state is plus y. So on the block sphere, you can see that I'm not able to reach exactly on my target state. It's slightly inward of the block sphere. This is because of the dissipation. But here you can see that for certain value of pulse time, which is optimal time, the fidelity is maximum, beyond which it decreases. So it is known in literature that there exists an minimum bound, theoretical minimum bound for beyond which you cannot, which guarantees you maximum fidelity. But here we are also saying that there exists a maximum bound as well. If you go beyond that, then the effects of dissipation comes into account, and which reduces the fidelity further. Now you may ask that these are the standard states from plus x to plus y. What about any random state? Does it work for that? And for that also I give you this, that this is any random state, and here also the story is same, that there exists an optimal time which gives me maximum fidelity beyond which it decreases, and here also I'm not able to exactly land on my target state on the surface of Bloch sphere. It is slightly mixed and it is inside the Bloch sphere. So the goal is not to reach on the Bloch sphere, surface of the Bloch sphere, but to reach as close as possible, because given the dissipation exists, you cannot go exactly on the surface. Okay, fine. Then these are the optimal pulse profile which we have found using the grape algorithm. And here you can see this blue one shows the y quadrature, which is U2, and this orange one is the x quadrature, U1. And on the y-axis, I'm showing the U by omega SL, meaning the scaled amplitude. So this is also dimensionless. And here you can see that the shape of the pulse profile is not very obvious or not very standard. It's neither Gaussian, rectangular, or square. This is any arbitrary shape. But this gives you the maximum possible fidelity in minimum possible time for both the cases, from going from plus x to plus y, as well as for this random state we have considered. Okay, fine, but if this, so far what I have said is theoretical. If I give this pulse profile to an experimentalist and ask to verify my theory, they will ask that how robust it is, because it's not possible exactly to give this pulse profile. So how much deviation can it handle? And for that, we varied the environmental correlation time. So this environmental correlation time is basically the dimensionless parameter which considers the effect of environment on my system, which is omega SL tau c. So we varied it from 10 to the power minus 5 to 10 to the power minus 1, 4 orders of magnitude, and here the color bar shows that. So here you can see the optimal pulse profile, this band for this 4 orders of magnitude is not very thick. And the corresponding fidelity you can see here, it is almost 100% till 10 to the power minus 2, and beyond which it falls and falls to a minimum of 88%. So this is the robustness for this part, and similar thing can be shown for this general case as well, for the random case. And here also the story is more or less same. And this I'm showing for the y quadrature. Similar thing is for x quadrature as well. Now, experimentally, it's also the case that you are not able to hit exactly where you want to. You cannot hit on resonance. There can be slight detuning. So how much detuning can it handle? And for that analysis, we did this. And here detuning, again, this is in the scaled unit. So this is also dimensionless. And it is from minus 3 to 3. And you can see that the fidelity is changing only after third place of decimal. And on the larger picture from 0 to 1, you can see that it is flat. And this is for both the cases. So for wide range of detuning and for wide range of environmental correlation time, it is more or less robust. Now we give the reason of optimality in the parameter space of pulse time and the environmental correlation time. And this maroon reason, this gives you the maximum possible fidelity for both the cases. And with that, I conclude that we have revisited the method to optimize pulse profile by incorporating environmental dissipation as well as drive-induced dissipation. And we show the robustness for wide range of parameters for environmental dissipation time, for environmental correlation time, as well as for detuning. And there exists an optimal time of evolution, which gives you the maximum bound as well on the evolution time, beyond which the fidelity falls. And this optimal pulse profile maximizes the fidelity, and this can be used to steer the quantum system from any given initial state to a target state. And so far what I have shown is considering the parameters for the transmon qubit, but this can be done for any quantum platform which can be represented as a two-level system. And with that, I would like to thank the organizers for giving an opportunity for the junior researchers like me to present our work on this platform. And also, I would like to thank all of you for showing up on the very last day of the conference. Thank you.
So, questions?
So about this optimal time, do you have some theoretical prediction on it, or is just a numerical?
Yes, so far what we have done is numerical, but the expression for evolution using grape algorithm. So for grape, you have to incorporate the dissipation channel at every step. So for that, we have an analytical expression. Yes.
Thanks. So you're modeling everything with a non-Lindblad master equation, I understand. Yes?
It is Lindblad, but this term, there is one term which is like, yes, this one. So this equation is kind of Lindblad, means it has the Lindblad structure. Here you can see this is Lindblad structure. This is Lindblad structure. This one term is coming which is kind of non-Lindblad, which is because of including the non-rotating wave drive term.
Right. Well, so is it Lindblad or is it not Lindblad overall?
Overall, it is Lindblad, yes.
Why do you say that? You can rewrite it in Lindblad form?
Yes, we can, because this can come as like sigma plus rho s term. Yes, it will come.
Okay.
Yes.
So I guess
for two-level system, it has been simplified to this.
Right. I think it would be clearer if you rewrote it in Lindblad form. Okay. So if it is in Lindblad form, yeah, then okay. I was going to ask a question about the size of the non-Lindblad parts, but if you say it is Lindblad, then that doesn't. Okay, thanks.
Thanks for this.
Is it working? Yes. So thanks for the talk. So there, I just want to make the point that there are, for arbitrary evolutions, no matter whether Markovian or non-Markovian, there's now formulated speed limits for open systems.
Yes.
So you could compare to these predictions.
Yes, that is our next step. Yes.
And
we are trying
just to make sure that you are reaching as well the optimal solution. Yeah.
Yes.
We are optimizing within your method, but it's to be seen whether this is optimal. And then also,
I understand. Yes.
There's a beautiful geometric understanding of the optimal trajectories that you could,
I have seen your paper.
explore.
Yes. On that, yes.
Good. Cool. Thanks.
Thank you.
So, any other questions? So if not, let's thank the speaker again.
Thank you.